Now we'll see one more problem, that is phantom phenomena. So what is phantom phenomena? First of all we'll see, and you realize that it is related to unrepeatable rate. That means unrepeated rate and this one are quite similar. We will see that. So this is transaction number 1. In that we are writing a query, select star from EMP where employee ID equal to 1, and select star from EMP where employee ID equal to 1. Same query is executed 2 times in one transaction. Second transaction is this one, insert into employee where values 1 comma Raju. In employee table you are adding one tuple called 1 comma Raju. So when you do that, what happens we'll see. First time when you execute this query, because there is no employee ID 1, then you get empty result. And second time when you execute it again, after this one, what happens? So insert into employee values 1 comma Raju, then 1 comma Raju will be added. Then when you execute it again, this time employee ID equal to 1 condition will be satisfied, and this time so you get 1 comma Raju. This phenomena is called phantom phenomena. That means, so as a transaction T1, if I am not aware of transaction T2, then I feel that when a same query is executed 2 times, I should get same value. But here I got some extra tuple, right? So this is called phantom record, right? Phantom record. But how it is, I mean, it looks like almost unrepeatable read problem, right? You are reading the data, and there is a difference in 2 reads, correct? That is unrepeatable read. So how phantom phenomenon is different from unrepeatable read, I will tell you. Usually unrepeatable read is about you have a database already, so no extra insertions, nothing, and you were reading same database item 2 times, but that database item is modified by someone. So unrepeatable read problem occurs generally in static database. That means no extra tuples added to your data. So consider this situation. This is your database, no insertions possible, let's say. In that also you get unrepeatable read problem. We'll see that. Example, you have database variable A. Okay, what is A here? A is maybe some part of record. Let's take this as employee ID 1. Employee ID field, and this is record number 1, whatever. So here you have employee name also. So we are talking about employee ID. Now you see, select star from EMP. So I am explaining you unrepeatable read problem. Select star from EMP where employee ID equal to 1, nothing first time. Okay, so assume that this one is 2 comma Rani. There is only one record. We are not adding any record. So in phantom phenomena, when new record is added, that will happen. But unrepeatable read problem is like this. You have 2 comma Rani tuple, and first time when you do select star from EMP where employee ID 1, nothing will be printed. Second time before this one, this is not insertion. So unrepeatable read problem is about updation. Example, if I update 2 comma, I am not writing the proper syntax, but just giving the rough idea. So let's say update 2 comma Rani to, let's say, 1 comma Rani. That means I am updating this 2 to 1. If I do that, yes, we know that we usually sometimes we update the tuples, correct? Then this will become 1. Now same query if it is executed, select star from EMP where employee ID equal to 1. Because of this updation, next time when you access this query, you get what? 1 comma Rani, right? First time empty, second time 1 comma Rani. This concept is called unrepeatable read. So here when you read 2 times employee ID, first time nothing is printed, but second time you got different answer. So that is unrepeatable read. So phantom phenomena almost same. So you have this question, sir, it looks almost same. Yes, almost same. But in phantom phenomena, the idea is because of new tuple. Example, so the phantom phenomena is about adding new records. If I add new records in between, then definitely you might get different tuples, correct? That is phantom phenomena. So usually phantom phenomena occurs when database has been improved or number of tuples are increased. That means when you add the data. Unrepeatable read problem is about not adding the data. So you may add the data, you may not, but definitely without adding also you get it. So existing data is updated, then I can say unrepeatable read problem might occur. Phantom phenomena occurs when you add a new tuple. That is the small difference between unrepeatable read and phantom phenomena. Understand? So these are all the various problems in transactions. So we have to avoid them. So sometimes if you like them, that means, if this is not a problem for you, that's okay. But sometimes you might see it as a problem. It depends on your requirement. So finally, so what is my idea is, so we have to eliminate all these problems. For that we need a mechanism, or we need a theory. We have to develop such theory. So we are going to do that. So first of all, what we do is we try to understand what are the essential properties every transaction has to possess. They are nothing but acid properties. Once we see them, then we'll go to the theory which is related to controlling this concurrency. Okay. Now we'll see acid properties one by one. So every transaction must possess these four rules. One by one we will see why they are so essential. First of all, atomicity. So atomicity is like this. You have a transaction T1 and it is having some instructions like this. Let's take one example. So that transaction is transferring the data from one account to another account, let's say A to B. So A is having value 50 and B is having value 100, and we are transferring this entire 50 to this side. For that we can write the data like this, code like this. Read A, and from A you remove 50. I know that here there is 50. Then after that I update it. Then I will go to B, I read it, and for B I add B equal to B plus that 50. Then I update it. This is what typical transaction for account transfer, right? 50 rupees is transferred from here to here. Now the question is, what is atomicity? Atomicity is like this. Either all the instructions should be executed, otherwise nothing should be executed at a time. That means whenever DBMS says that it is executing transaction, so either all the instructions should be executed, no problem. Otherwise nothing. But it should not execute some of them and it should not leave some of them. That is what atomicity. So here one funny argument by DBMS will be like this. So example, DBMS is saying like this: something is better than nothing. So I am executing 50% of the instructions. This is DBMS argument. I don't like atomicity. What I do is, whenever I can do execution, I do. That means if I can execute 50% also, I do, and I say something is better than nothing. So that won't work here. The reason, when you do 50% of the code, what is happening is, let's say these two are your accounts, then 50 rupees is removed from first account, you get 0. Then after that, let's say power goes off. That is the reason it was not able to complete the transaction. Then so still B shows 100. Do you want this kind of execution? No, no one is ready to accept this kind of scenario. That's why atomicity is very important. Either entire this 50 should be transferred, otherwise nothing should happen. But it should not be like that, where 50 amount is removed from here but it is not added here. That kind of things will happen if you have done only half of the instructions, correct? That's why atomicity is very essential. So either all the operations should be performed, otherwise nothing. So simple. So in DBMS we have a component called atomicity manager. So that atomicity manager, otherwise in some literature or in some authors say that it is transaction manager. So transaction manager takes care of that atomicity idea. Okay. Now we'll see consistency. So in high level I can say that database maintains it. Now we'll see consistency. In consistency, this is the idea. You have two transactions, or otherwise you have a transaction. So before executing transaction, you have a database state, let's say state 1, and after executing transaction 1, so this database state is changed to S2. What is the meaning of database state? All the collection of data and their values, correct? Now example, so in state number 1, there is a database variable A, its value is 50. Then here this database variable A's value might change, correct? So that's why two different states. Now whenever you execute a transaction, database should go from one safe state to another safe state. That means, so is initially I assume that, let's say database is in consistent state. If this database is not in consistent state, then this is not good idea, right? That is not good design. First assume that, let's say your database is correct. That means consistent. Now after executing transaction T1, if it goes to another state, it happens, then that database also should be in consistent state. That means it should not have any discrepancies, otherwise it should not have any problems. That is called consistency. So your database should go from one consistent state to another consistent state. So please show us one inconsistent state. I will show you. Example, let's say this is your program or transaction T1, right? So you are writing read of A and A equal to A minus 50, and you are saying that this is account transfer program. Account transfer program. So in that you are reading A, we know that how to do the account transfer. Just now we have seen, correct? Its initial values are 50, 100. So let's remove 50 and update it. But second time, when we know that when you remove 50, we have to add 50, right? So you did this one. So read of B and B equal to B minus 50 and write of B. Yes, whoever watching this video slowly understanding that I am doing mistake, correct? That is what. So if I do this, then really it is account transfer program. What is the consistent value of, what is the consistent value? A plus B definitely should be some constant. Example, initially A plus B 150. Then after doing in this transaction also, the sum should be 150. The reason is what you are doing after all account transfer. Whenever you do account transfer, then in this way, if you write this code, A will become 0, B will become what? 50. So sum will be just 50, not 150. What's the problem? Your code is wrong. So because of your wrong code, so you get inconsistent state. That's why consistency has to be maintained by programmer. Otherwise, the person who writes transaction, that is programmer, or the user's responsibility. Consistency is user's responsibility. Atomicity is database responsibility, especially transaction manager, otherwise atomicity manager. Now we'll go to isolation. What is isolation? Isolation is like this. There are some set of transactions which are going to be executed in your machine. Now, after executing them, isolation says like this. Example, transaction T1 is getting executed. The result should be like, it is though it is executed in parallel world, that in concurrent world, but the output should be in a way that it is executed alone. Let me revise again. So isolation is like this. When multiple transactions are concurrently executed, though, but the effect of one particular transaction's execution should be like it is executed as a single, otherwise alone. So let me explain with picture. So this is your transaction T1 and T2, T3 are the other transactions. Now, though you are executing in a computer where multiple transactions are context switched, that means sometimes T1 getting executed, sometimes T2 is getting executed, sometimes T3 is getting executed, but the output of T1 should be, that means because of T1, whatever the database, example, there is no T2, T3, what is the database state? The same thing should happen if this T1 is executed in the concurrent world. That means if it is executed alone, whatever the result it gets, same thing it should get. But because of this concurrency, T2, T3, they should not disturb this transaction T1. They should not interfere with transaction T1's activities. Then we say that we are maintaining isolation property. That is very essential property. For that I will give you analogy. Example, let's say you are preparing for GATE. Okay. So this is one classroom, right? So in this classroom, so one faculty is teaching the class. These are all the students. Now everyone is attending the lecture seriously, right? Now after this entire course, the student number 1 got rank 1000. Now his claim is like this: if I have prepared alone, that means without this B comma C comma D, let's say this is A, B, C, D. If B, C, D are not attended this GATE session by this faculty, something like F, okay. This is argument of A, listen. A is saying that if B, C, D were not available in the class, if I am the only person who attended this class, then I would have got rank 1. That is his argument. So that means what? His actual capability is getting rank 1. He can get rank 1. And he only gets rank 1. But because of other students, he is getting 1000. That means what? He got disturbed by this B comma Z comma D. Then we say that, so his execution is not same as, his execution in this concurrent world is not same as his execution in serial, otherwise alone. That means when he is executed as alone, correct? So then we say that he is violating the isolation property. So in isolation property, so finally what I want to say is your transactions output, whatever it the transaction represents or whatever the output it gives, whatever the variables it modifies, the same thing should happen. I mean, whatever it modifies, it should not be disturbed by other transactions. So that is called isolation. Usually, so when you are in concurrent world, other transactions might disturb you. Already we have seen it, right? So in one line I can say that this kind of problems we should not get. Phantom phenomena, otherwise unrepeatable read, otherwise lost update, otherwise dirty read. All these problems are because of execution in the concurrent world, right? So isolation is very important property we should remember. Somehow we have to maintain the isolation. Who will maintain it? How can I know? How do I know that? So I know that others are going to disturb me. I don't have clue, right? So that's why that is a problem with not transaction. It's a problem with multiple otherwise concurrent execution. So while writing transaction T1, that user doesn't know that T2, T3, T4 will be in the picture and they are going to affect this T1. That's why DBMS should take the responsibility and DBMS should avoid these problems. We know that, correct? So how DBMS should avoid? For that, DBMS has a software wing, otherwise software module. So usually the name of that module is, concurrency manager. So DBMS concurrency manager is going to handle this isolation property, and it is very essential property because of other transactions. If your transaction gets disturbed, so definitely that is a serious problem. We don't want such situations, right? Example, let's say you went to a bank. In that bank, let's say you want to add some 1 crore to your account, but if you go alone, if there is no one in the bank, then you can add 1 crore easily, let's say. But when multiple people are, this cashier, whoever is taking your 1 crore, so if there are multiple people disturbs him, other transactions, he's not going to handle it properly. Let's say what he spoils your 1 crore. What if that 1 crore he will throw out somewhere because of this concurrency? Definitely you will bother, right? So that's why isolation is essential property like atomicity and consistency. Now we'll see durability. So durability is different from these other three properties. What is durability is, in durability, so we have to maintain the data permanently. That means when transaction T1 modifies some database item, then the modification should be permanent. Permanent means not 1 year, not 2 years, not 3 years. It is forever. Theoretically, durability means maintaining the data forever, updations forever in that way, unless others modify it. I'm not saying that, example, there are two writers. So transaction T1 is writing database item A, transaction T2 is writing database item A. Obviously, T1's write will be cancelled because of T2. That is perfect. So I don't have any problem with that. But when there is no other write of A, if this is only the write of A, now in such case, after some time, example, really the database, your DBMS executed T1 and it stored whatever the value you have given, that means given by transaction T1. Example, this write of A is writing 20 here. But after 1 hour, what happened? Because of its personal problems. Personal problems means power failure. Maybe after when you write of A, so when that write of A operation was executing by your database, if power goes off, otherwise earthquake occurs, otherwise tsunami occurs, otherwise your disk completely failed. Whatever may be the case, you are going to lose the data, but that should not happen. So that is called durability. So durability will be maintained by a software module in DBMS, that is recovery manager. So when this kind of failures occurs, this is called failure. So when you cannot retain the values in your database, that is failure, then the failures can be handled by recovery manager, right? So we will see most of the time, especially for gate, we are going to focus on isolation property. So consistency is quite easy because user has to write the right program, very easy. Atomicity, so database maintains it, and durability, database maintains it. Isolation also, database maintains it, but three different software modules, and especially we are going to stress on isolation. So concurrency control. So 80% of the topics related to isolation property. We will see that. Now we'll see a concept of recoverability. So what is recoverability is, it's a theoretical notion. That means, we are defining some theory related to, recoverability. That means what is recoverable schedule and what is non-recoverable schedule. First of all, see the definition of recoverability. After that, you try to understand what is the purpose of it. So recoverability concept says, otherwise it defines two different things. One is recoverable schedule. Second one, non-recoverable schedule. I will tell you what is schedule. Non-recoverable. First of all, schedule is nothing but some set of transactions and they are ordered based on timeline. That means, example, whenever I say I have a schedule, then I have transactions and their instructions, but they are ordered based on their timings. Example, let's say read of A of T1, we assume that let's say T1 has read of A, T2 has read of A, let's say T3 has read of B. Then this is 9 o'clock, that means T1's read of A is executed at 9 o'clock, this is executed at 10 o'clock, this is executed at 11 o'clock in the system. If you have this information, then we say that we have schedule. Schedule is set of transactions whose instructions are arranged in a timeline. And our simple assumption is no two transactions instructions will have same time. That means we never see in schedule this kind of thing. That means, so read of A at a time. It will not be possible for us to develop the theory. So we always assume that, so we have only one single system. In that single system, either transaction T1's instruction will be executed or T2's. In that way, if you assume, then you never get that kind of situation. Okay. So let's assume that to develop this theory. So what is recoverability? So recoverable schedule is a schedule where in that schedule no committed transaction need to be rolled back. Let me write the definition. So in recoverable schedule, no committed transaction need to be rolled back. Now non-recoverable schedule. So non-recoverable schedule is nothing but, simply which is not recoverable. So it is very easy to understand which is not recoverable. So let's focus on recoverability. That means recoverable schedule. If you understand recoverable schedule, automatically you can understand non-recoverable schedule. That's why I don't want to bother about this non-recoverable schedules. So recoverable schedule is such a way that no committed transaction in that schedule has to be rolled back. If you get that kind of situation, so why you get that kind of situation? Example, let's say to have consistent database. So sometimes you have to cancel some transactions and sometimes you might need to cancel committed transactions. If it happens, then this condition will be violated. Remember, this is very important. No committed transaction need to be rolled back. We'll see some examples. So, and we will check whether that schedules are recoverable or not recoverable. Let me do that. See these two examples and we'll see whether these schedules are recoverable or not. First of all, if you see, T1 is reading the data base item A and after that it is updating it. Remember it, that updated value is taken by T2, correct? So this is called dirty read. Whenever there is a dirty read, you remember, always this recoverability problem arises. So now this is dirty read. I'm not saying that always it is not recoverable, but recoverability question arises only if you read dirty data. So what happens if you read dirty data? We will see. After that you are writing it and you are updating it, correct? So after that, if you see at this point, now this transaction got cancelled. That means whatever you read it here, that was wrong. So when you read wrong data, then how to correct the system? For that we have to cancel T2. For that, I take A value something and I explain you. A value initially, let's say 100, and this A transaction T1 is incrementing it by 100 and transaction T2 is incrementing that by 200 in this scenario. So initially A value becomes 200. That is wrong data because it is however going to be cancelled. Because I know the future, I'm telling that at this moment. So your DB doesn't know. Assume that for simplicity, what really your database updates immediately whenever you do some updation. So your database is getting updated. Okay. So then A will be getting 200. Now after that you see read of A, write of A. So now this read of A is going to see what? This updated value. That is what our assumption. Okay. So if that is the case, read of A reads 200 and A equal to A plus 200, then that will become 400 and you are going to update 400. So that 200 is correct, then only 400 is correct, you remember it. Then after that you said commit, then transaction T1 got rolled back. Whenever T1 gets rolled back, then whatever you have taken, that 200 is wrong. Then hence your 400 is wrong. So finally we have to cancel T2 also, right? Otherwise we can't, so we can't get it correct, because this transaction T1 should be cancelled, then hence T2 should be cancelled. The reason, clearly you are taking the wrong data. So we have to be, we have to cancel it. This is called, you know, non-recoverability. Why it is non-recoverable? This is committed transaction. What are you doing? You are rolling back it. You have any other option? No, you don't have any option. So to make the system correct, so committed transaction need to be rolled back here, but according to recoverability definition, no committed transaction has to be rolled back. But here you are getting that situation. That's why it is not recoverable. Now we'll see here. So some students think that, so this is recoverable. Why? Both are committed transactions. No. Though there are two committed transactions, still recoverability case arises. You see, non-recoverability. Example, again there is a dirty read. That means you are reading the wrong data. So after that you have committed. So once you commit this one, then you are going your house, right? Transaction T2, imagine like a person. So once this transaction T2 is, done, then T2 is going to house. Then after that, here you see this point. Anything can happen in the world. Then at this point, if power failure occurs, then I'm talking about. So if power failure occurs here, so it is not committed transaction. It is future, right? So this is set of transactions I have given as a list. But 9 o'clock read of A will be executed, 10 o'clock write of A will be executed, 11 o'clock read of A will be executed, 12 o'clock write of A executed. So far your DBMS doesn't have clue that whether power failure occurs or not, correct? So at 1 o'clock, let's say this commit happens, then this transaction T2 will be committed transaction. Now 2 o'clock power failure occurs. Now we have two transactions. One is not completely executed, second one completely executed, and even it is committed. So now such committed transaction, really your DBMS makes, if it agrees that it is committed transaction. Yes, sometimes it may agree, correct? The reason 1 o'clock this T2's commit happened, and assume that, let's say, if your database management system accepts it, that means it executes commit instruction and 2 o'clock power failure occurs, then we have to cancel this transaction. We don't have any other option, because this is partial transaction by this point, correct? So though you are seeing commit, it is future instruction, correct? So it is not executed by your DBMS so far. So at that point, yes, it might, this case might occur. What is that? This power failure, because of the transaction T1 has to be cancelled and T2 has to be rolled back or cancelled. We have to cancel it. Think about it. Why? Since this is wrong data. When you take wrong data and whatever you do, then that is wrong, right? Then to correct the system, we have to roll back transaction T2 to original state. Understand? For that, again, committed transaction need to be rolled back. In these two cases, so your schedule is not recoverable. Understand? And one important point I will tell you, for easy recognition, given a schedule, whether it is recoverable or non-recoverable is the question. Remember one thing. So if whenever you take the dirty data or wrong data, don't commit before the other transaction. That is a problem. If you don't commit, remember from now onwards, take the dirty data, no problem. And if you want to be safe and safest, don't read dirty data. Let's suppose you have read, still no problem. Your schedule can be recoverable according to theory, but for that, never commit it until T1 is committed. If T1 is committed, then only T2 should be committed. Example, this is the point where T1 gets committed. Then after that only this T2 has to be committed. Remember it. If you see this kind of order, that means whenever T2, a transaction reads dirty data from T1, then this transaction T2 who read dirty data, its commit should be after the transaction from which you have taken the dirty data. Understand? If this is the order, if T1 gives dirty data to T2, then the commits order should be same way. Then definitely it is recoverable. Here you see commit order is different, right? Reverse. Then definitely it is non-recoverable. In this way, easily we can find out whether a schedule is recoverable or non-recoverable. Okay. Now we'll see recoverable schedules and further classification. So recoverable schedules again into cascadeless and cascading rollback. What is cascading rollback schedule is? So cascading rollback is recoverable, but to recover the schedule we have to cancel lot of transactions, otherwise we have to roll back lot of transactions. We'll see with examples so that easily you can understand. Consider these three transactions T1, T2, T3 and write off here, read off here, write off here, read off here, write off here, commit, commit, commit. First of all, we'll see whether it is recoverable or not. In a recoverable schedule, no committed transaction need to be rolled back, correct? First of all, you see there is a dirty data. Now here there is a dirty read. Whenever there is a dirty read, that whoever done that dirty read, that should not be committed before the transaction from which it is read dirty data, correct? So here T1 is giving the dirty data, correct? Then after T1's commit only, if T2 commits, there will be definitely no recoverability problem. That means it is recoverable so far for these two. Now here you see again, so dirty data. Whenever there is a dirty data, the order of commit should be exactly in the order from, so I can say that since T2 is giving the dirty data to T3, then the commit order should be T2 to T3. So finally, both conditions are satisfied here for this dirty data, this dirty data. Now I can say that this is recoverable, but in this recoverability, so there is a cascading rollback. So this is actually cascading rollback schedule. The reason we will see. Now example, power failure occurs here. Think about it. See here. When power failure occurs here, because in these problems we should assume power failures, otherwise catastrophic failures like tsunami, otherwise anything at any point of time. So it's about possibility. If there is a possibility here where power failure occurs, then we have to see the scenario. Then since you read the dirty data, first of all T1 will be rolled back. That is compulsory because we don't know whether T1 is partial transaction or complete transaction. So when power failure occurs here, we cancel T1. When we cancel T1, since T2 took dirty data from T1, T2 should be cancelled and hence T3 should be cancelled because T3 also took dirty data from T2, correct? So now, but at least these transactions are not committed transactions. So since they are not committed transactions, I don't have serious responsibility that I have to maintain the safe state, otherwise I have to store the results permanent. Recall commit definition. Whenever a user writes commit statement and if you say that yes, I executed it. If whenever DBMS says that my dear user, I have seen your commit and I am following it and I executed it and it is done. When it says like that, after that database result should be permanent. But here we are happy because if power failure occurs here, then we should not, DBMS should not answer anyone because all are partial transactions by that time. So they can be cancelled, they can be done anything. So that's why I can cancel this, I can cancel this one, I can cancel this one. That's not a mistake. But unnecessarily you are cancelling lot of transactions and that takes lot of time. And see, maybe transaction T2, imagine it's very big transaction and since early morning it's getting executed and it used lot of resources of computer. Suddenly now you are cancelling entire transaction. So then you are wasting lot of computer resources and sometimes some human time also, correct? That's why cascading rollback is definitely not good. We should avoid it if possible, right? So now I can say that this is cascading rollback. Since there is such possibility, then you don't require to check power failure everywhere. If you have one case where if you show that the transactions has to be cancelled, if you show such situation, that is enough. So I don't think, some students argue like this, sir, power failure occurs here, okay, then this is committed transaction, this is committed transaction, this is committed transaction. So this data is correct, so these transactions operations are correct. Since this data is correct, then these transactions operations are correct. Everything is correct. Yes, when power failure occurs here, everything is correct. But power failure occurs here, not everything is correct. So we should do definitely cancellations. So we have to see a possibility. None, I'm not saying that we have to check everywhere. If there is at least one possibility where you can show that cancellation should be done, then we say it is cascading rollback schedule, right? Since I'm showing one possibility here, it is cascading rollback. Now, other case is cascadeless. Cascadeless is opposite to cascading rollback. It is a recoverable schedule, but not cascading rollback. That means to recover it, you don't require to cancel the transactions. Now we'll try to do post-mortem. Actually, what is the need of why you are getting into this situation again and again? What was the problem? Dirty read. If you don't do dirty read, you never, I mean, your transaction need not be rolled back at any time. You never get that kind of situation. This transaction T2, transaction T3 are becoming victims. The reason they are taking dirty data. If they don't take dirty data, no one will cancel them unless they have some mistakes in their own transactions, right? So, and some students understand this in a wrong way. They say like this, sir, if there is only one transaction T1 and it is having read of A, write of A, and there is a commit whatever, and they ask like this, sir, power failure occurs here. Okay, then we have to cancel this transaction, right? Yes. Is it not cascading rollback? No, it is not cascading rollback due to others. Otherwise, remember dirty data. Whenever you read the dirty data, because of that your transaction has to be cancelled. That is called cascading rollback. Now we'll see cascadeless schedules, how they look like. See now, so wherever power failure occurs, because all transactions are, I mean T2 and T3 are just taking only non-dirty data, because before this read operation, T2 takes data from, of course, T1, because T1 is updating A, right? But whenever you read that data which is updated by T1, that is committed transaction. When it is committed transaction, then the database will have permanent value. That means, it is correct data, right? So we never cancel T1. If and all if we cancel T1, it's all theory, right? Don't ask me this question, sir. After commit also, if your DBMS is not able to, retain the value of T1, and if still T1 is cancelled, so in theory, so that is not possible. In implementation also, no DBMS should do that. Committed transaction never need to be rolled back. Okay, remember it. So I am seriously assuming that whenever a transaction commits, and if that transaction is executed by a DBMS, definitely that DBMS is going to store its data permanently. Okay, so that is one of the property of ACID properties, correct? Durability. So that's why. And second thing, since it is now correct data, we are sure. Now if this data is taken by T2, that's never will become mistake, correct? The reason is it's not dirty data, right? So now what if power failure occurs here, sir? Then you have to roll back T1, that quite obvious for every transaction. Then by that time, since T2 and T3 are not at all reading your data, they are in safe state. This is the point they are reading your data, correct? Here, right? Here power failure occurs, since they are not committed, no responsibility for DBMS. If power failure occurs here, now it is committed transaction, but before that this T1 also committed and it is taking valid data, there will not be any problem. If power failure occurs here, see all possibilities, that's it. If power failure occurs here, so what? It is, non-committed transaction, correct? And it has to be rolled back because of, just normal power failure. It's not because of your dirty data reading, right? So there is a difference between these two. Here we are cancelling transaction T2 because he read dirty data. But here there is no dirty data, there is no question, right? If and all if we cancel the transaction because we are in between, that is the only reason we cancel. Apart from that, due to T1, are we cancelling T2? No, we never get that kind of situation. The reason, so T1 is the only way we cancel T1 at this time. At that time we are not reading, but we are reading at that time already T1 is committed. Then committed data we can take, not a problem. Finally, in one line I can say that, so whenever you read committed data, that means T1 is updating A and it is committed, and you are taking that data, you never get any problem. You never need to be rolled back because of T1. Understand? So that's why we never need to roll back because of T1. T3 also never need to be rolled back, because though he is taking data from T2, but it is committed before you take the data. That's why this is definitely cascadeless rollback. Now I will give you one shortcut. That is, whenever you have dirty data, that means ensure that there is no dirty data. That's it. If you don't read dirty data, definitely that schedule is cascadeless. So simple. Now, if you read the dirty data, then your schedule might be recoverable, non-recoverable. So, how to make it recoverable? Whenever you read dirty data, at least please do this thing. What is that? Your commit order should be in this order. Example, T2 reads data from T1, then commit order also should be T1 to T2. Understand? So finally, this is about cascadeless cascading rollback. This example and we check the recoverability issues. First of all, we start with this one. So here there are two database items, one is A, one is B. Now we have to focus on dirty reads. Only because of dirty reads everything, this concept is evolved, recoverability. That's why focus on directly dirty reads. Write A to read A, dirty read. Now write B to read B, dirty read. Now after dirty read, now see the commits. So here this is one commit, this is one commit. The order of the dirty read is from T1 to T2, correct? So commit order also should be same. Yes, correct. Then here also write B to read B, commit order should be same, that means T2 to T3, but commit order is reverse. So here because of this database item B, so this schedule is not recoverable, because you know the understanding. When power failure occurs here, then by that time, so transaction T2 was not committed and it is partial transaction, then when power goes off, then T2 will be rolled back. To rectify the things, T3 will be rolled back, but it is already committed at that time. So committed transaction has to be rolled back. That is a violation of recoverability. This is non-recoverable schedule. Now we'll come to this one. Is it recoverable or not? Again, same story. Dirty reads. Yes, this is dirty read. Now again write here to read a dirty read. That's it. Two dirty reads. Now first dirty read, if you see the commit order, commit. Yes, correct order. So no problem. But now see here, write to read. So order T2 T3. Now focus on commits, but this is not commit. If this is commit, we have to see the order. If this is rollback, what I want to see is, so actually when you get problem, any transaction reads dirty data and there is a danger that if it is committed before the transaction from which it has taken the data, if that is committed after this one, then you get problem, right? That means here there is no such situation, because T3 is not at all committed transaction. If this is committed, then we have to roll back it, but already it is getting rolled back by itself. That's why there will not be any problem. So now are you seeing any committed transaction which has to be rolled back? Since it is not committed transaction, nothing to worry. So we don't need to worry about this dirty read. Now here the order is same. This committed transaction need not to be rolled back. The reason, the commit order, correct? So we have that kind of idea, right? So now finally this is recoverable. But to recover it, I mean, should we do cascading rollback or cascadeless? That's a question. Now is this schedule cascading rollback or cascadeless? How to check? In cascadeless, first of all we'll check whether it is cascadeless or not. If any recoverable schedule is not cascadeless, that is cascading rollback. So what is the definition of cascadeless rollback? Cascadeless. So in cascadeless schedule, you never need to roll back any schedule. So for that, you should not have any dirty read. Now your problem is reduced to, do we have any dirty read? Let's check. This is dirty read, correct? Before it gets commit, you read it. That's why this is dirty read. Now when there is a dirty read, that cannot be cascadeless, but recoverable schedules are either cascadeless, otherwise cascading rollback. So this is definitely cascading rollback. So in that way easily we can answer questions related to recoverability, right? Whether recoverable or non-recoverable, cascadeless or cascading rollback, everything. Now one more thing I would like to tell about cascadeless schedules. So in real life usually we prefer cascadeless schedules, because when you allow cascadeless schedules, they will not have any rolling back or anything. So you are not cancelling the transactions or existing transactions. Because of that, computer resources will be saved. But the problem is, whenever you go for cascadelessness, then what happens is we have to put lot of restrictions on your transactions. Then concurrency will be reduced. That is what the problem. So and finally either cascading rollback or cascadeless schedules, both are really good if you compare with non-recoverable schedules. But at any moment we should not allow non-recoverable schedules because their committed transaction has to be rolled back. So that is very dangerous thing. Generally it is not preferable. This is about the schedules. Okay.